6.2 Conditional distributions. Table 6.1 contains much more information than the two marginal distributions of sex alone and degree alone confer. Marginal distributions tell us nothing about the relationship between two variables. To describe a relationship between two categorical variables, we must calculate some well-chosen percentages from the counts given in the body of the table. Let's say we want to compare the proportions of women and men who receive a professional doctorate degree. To do this, compare percentages for each sex category. To study women, we look only at the women row in Table 6.1 to find the percentage of women who receive a professional doctorate degree. Divide the count of such women by the total number of women, the row total. Women who receive a professional doctorate degree divided by row total equals 97 divided by 2,283 equals 0.042 equals 4.2%. Doing this for all four entries in the women row gives the conditional distribution of degrees conferred among women. We use the term conditional because this distribution describes only students who satisfy the condition that they are women. Conditional distributions. A conditional distribution of a variable is the distribution of values of that variable among only individuals who have a given value of the other variable. There is a separate conditional distribution for each value of the other variable. Statistics in your world. Smiling faces. Women smile more than men. The same data that produce this fact allow us to link smiling to other variables in two-way tables. For example, as the second variable, add whether or not the person thinks he or she is being observed. If yes, that's when women smile more. If no, there's no difference between women and men. Next, take the second variable to be the person's social role. For example, is he or she the boss in an office? Within each role, there is very little difference in smiling between men and women. Example 6.3. Comparing women and men. State, how do women and men differ in terms of the degrees they are projected to receive in 2000 to 2021? Plan. Make a two-way table of response by sex category. Find the conditional distribution of response for each sex category. Compare these two distributions. Solve. Table 6.1 is the two-way table we need. Look first at just the women row to find the conditional distribution for women, then at just the men row to find the conditional distribution for men. Here are the calculations and the two conditional distributions. Okay, so in this table you can see they've taken the the value for each condition and divided it by the total number of observations to get a percentage for each of the, in this case, 8 categories. The percentages in each row should be 100% because for each category, everyone receives one of the 4 degrees. However, in general, the percentages may not add exactly to 100% because we round off to a fixed number of decimal places. This is round-off error, and we see that there is round-off error here. Conclude, the percentage of women projected to receive an associate's degree is higher than the percentage of men projected to receive an associate's degree, while the percentage of men projected to receive each of the degrees, other than an associate's degree, is slightly higher than the percentage of women. Round-off error. The round-off error is the small difference between a rounded decimal number and its precise value before rounding. Software can do these calculations for you. Most programs allow you to choose which conditional distributions you want to compare. The output in Figure 6.2 presents the two conditional distributions of degrees conferred, one for each sex category, and also the marginal distribution of degrees conferred for all the students. The distributions agree, up to round off, with the results in examples 6.2 and 6.3. Remember that there are 2 sets of conditional distributions for any two-way table. Example 6.3 looked at the conditional distributions of degrees conferred for the 2 sex categories. Figure 6.3a makes this comparison in a bar graph with separate bars for men and women, side by side for each category of degree. In this graph, the total of the 4 blue bars is 100%, and the total of the green bars is also 100%. We could also examine the 4 conditional distributions of sex, one for each of the 4 categories conferred, By looking separately at the four columns in Table 6.1, page 161, Figure 6.3b makes this comparison in a bar graph, again with separate bars for men and women side by side for each category of degree. Note that the percentages for each side-by-side pair add to 100%. Figure 6.3c also makes this comparison. In C, each bar is segmented into two parts, represented by two colors. The upper portion of each bar represents the proportion of women who receive each degree. The lower portion represents the proportion of men who receive each degree. Each bar has a height of 1 because each bar represents all the students in each different group of people. Bar graphs like that in Figure 6.3c, in which each bar is divided into parts, each bar representing a different category, are sometimes called segmented bar graphs. Segmented bar graph. A segmented bar graph is a bar graph for presenting data about two categorical variables in which each bar is divided into parts. Each bar represents the observations that take a particular value of one variable, and the length of each part of the bar represents the proportion of those observations that take a specific value of the second variable. Figure 6.2, Minitab and JMP output for the two-way table of adults by sex and education. Each entry in the Minitab output includes the count and percentage of its row total. The men and women rows give the conditional distributions of responses for each sex category, and the all row shows the marginal distribution of responses for all these adults. Notice that Minitab and JMP order variables in the table alphabetically. Each entry in the JMP output includes the count and percentage of its row total. The second entry in each cell gives the conditional distribution of responses for the different sex categories. The total row and column show the corresponding marginal totals of responses for all these adults. Okay, so you can see that in this two-way table that has been produced by software, not only do you have the counts in each little cell, but you also have the percentage for each cell, which makes up the conditional distribution. Then you still have the marginal totals under all. And the second type of software gives a very similar output. Figure 6.3a, side-by-side bar graph comparing the percentages of women and men among those in each sex category for each degree conferred. Okay, so you can see in this first of three bar graphs, they're showing the percentage of total men with degrees out of 100% of the four types and the percentage of total women with degrees out of the four types. So then they're comparing, like if you look at the first set of bars that have the associates degrees together, the blue bar for men means that 24.8% of the total number of men who got degrees conferred were associate degrees, and the green bar touching it for women's associate degrees is 28%, and that means that 28% of the 100% of women who received degrees received associate's degrees. So this is showing the conditional distributions graphically, and it's the percentages of men and women in each sex category for degrees conferred. Each percent is the value in the two-way table cell divided by the total number of observations in one of the variable categories, in this case sex. You can see this by doing the conditional distributions and seeing that the percentages match up. Okay. Figure 6.3b, side-by-side bar graph comparing the percentages of women and men among those in each degree conferred category. So this one is showing what percentages of each category of degrees conferred was to men or women, and it's a direct comparison between the bars. So each percentage is the value in the two-way table cell divided by the total number of observations in the other variable category. Here it's the type of degree conferred. So these two bar graphs together show one variable by the other, and then the second variable by the first variable. So this is like the opposite table in a sense to the first, but they look very similar. On the x-axis in both, you have the four types of degrees, and the y-axis in both, you have the percentages. But so in the case of the percentages of men and women in each degree conferred category, you're dividing the values by the marginal totals to get the bars percentages per category. So if you look at the two matched bars of the men's and women's associate's degree, they will equal 100%. So 61.4% of the people who got associate's degree in these observations are women and 38.6% are men. C. Segmented bar graph comparing the percentages of women green and men blue among those in each degree conferring category. So this is the same as the second bar graph but stacked, which shows what percentage of degrees conferred was to men or women, and it's a direct comparison between bars which equal 100. So if you look at the first bar of associate's degree, the blue part at the bottom is 38.6%, which means that of the people in the observations who got an associate's degree, 38.6% of them were men, and on top of that is a green bar touching it on top of it, and that's 61.4%, which means that 61.4% of the people who received associate's degrees in these observations were women. Figure 6.4 shows a mosaic plot, which is a variation of a segmented bar graph. The bars now have different widths, and these widths correspond to the proportion of students in each of the 4 degree categories. Thus, the widths display the marginal distribution of degrees conferred. Each bar is again segmented into 2 parts, represented by 2 colors. The upper green portion of each bar represents the proportion of women among students who receive each degree. The other portion, blue, represents the proportion of men. Each bar has a height of 100% because each bar represents all the adults in each different group of people. The mosaic plot is more informative than the segmented bar plot because it displays the marginal distribution of degree conferred as well as the conditional distribution of sex given degree conferred. Mosaic plot, a segmented bar graph in which the width of each bar represents the proportion of all observations that fall into the category that the bar represents. Figure 6.4 displays only one of the 2 sets of conditional distributions. We would need another graph to display the other, the conditional distribution of degree conferred given sex. Also, the graphs in figure 6.3 and 6.4 only indicate percentages or proportions, not total counts. No single graph portrays the form of the relationship between categorical variables, as a scatterplot does for quantitative variables. No single numerical measure, such as the correlation, summarizes the strength of the association. Bar graphs are flexible enough to be helpful, but you must think about what comparisons you want to display. For numerical measures, we rely on well-chosen percentages. You must decide which percentages you need. Here is a hint. If there is an explanatory response relationship, compare the conditional distributions of the response variable for the separate values of the explanatory variable. If you think that sex influences degree conferred, compare the conditional distributions of degree conferred for each sex category, as in example 6.3. Figure 6.4, mosaic plot comparing the proportions of women green and men blue among those in each degree conferred category. Apply your knowledge. 6.3, video games and grades. Exercise 6.1, page 162, gives data on the grade distribution of boys who have and have not played video games. To see the relationship between grades and game playing experience, find the conditional distributions of grades, the response variable, for players and non-players. What do you conclude? The percentage of boys who played games and received A's and B's is higher than the percentage of boys who never played games and received A's and B's, whereas the percentage of boys who never played video games and received grades lower than A's and B's is slightly higher than the percentage of boys who played games and received marks lower than A's and B's. If anything, players have slightly higher grades than non-players, but this could be due to chance. 6.4, ages of college students. Exercise 6.2, page 163, gives U.S. Census Bureau data describing the age and sex of all American students enrolled in college. We suspect that the percentage of women is higher among students in the 25 to 34-year-old age group than in the 20 to 24-year-old age group Do the data support this suspicion? Follow the four-step process as illustrated in example 6.3.